for AP Calculus on the topic of optimization problems. So this one says an ice skating rink consists of a rectangle with a semicircle on each end. Given a perimeter of 1,000 feet, find the radius that will maximize the area of the rectangle. All right, so let's first label our diagram. Anything that involves something circular, we're going to use R as many places as possible. So there would be the center if it was a whole circle. So R is right there and right there, as well as on this side. R is there and right there. And then since this is half the circumference of a whole circle, this would be pi r from right there to right there. And the same thing over here. The whole circumference is 2 pi r, so from there to there would also be pi r. Now, if it was a square instead of a rectangle, then since this side is 2r, this side would also have to be 2r. But in this case, it's not a square, it's a rectangle, so we need another variable from here to here. I'm just going to use x. So usually the most number of variables you need on your diagram is 2. Usually that's the most you'll need. If you have 3, you probably use too many. So now, let's figure out first what we're trying to minimize or maximize. In this case, it says the maximum area of just the rectangle, notice, not the entire ice skating rink. So that's going to be our main equation, whatever you're trying to minimize or maximize. So the area of that rectangle is just length times width. But in this case, notice this side is 2r and this side is x, so it'd be 2r times x. So since this is what we're trying to maximize, this is what we eventually want to find the derivative of. But we don't do that yet because it's in terms of 2 variables. We need to get rid of either the r or the x. So there must be some other information we're given that can help us remove one of those variables with substitution. In this case, it's the perimeter of 1,000 feet. So perimeter just refers to just the outside. So that tells us 1,000 would equal, notice the perimeter here, be x plus x is 2x, plus pi r plus pi r is 2 pi r. And now we use this equation, we can isolate either the x or the r and substitute in to get rid of either the x or the r. So in this case, they're both fairly easy to solve for. I think x is a little easier to isolate, so I'm going to isolate that. So I'm first going to subtract the 2 pi r. So 1,000 minus 2 pi r equals 2x. And then divide by 2. So you can leave it as a single fraction like this, or you can split it up, especially on this one since both of them divide evenly. It's probably easier if we split it up. So 1,000 divided by 2 is 500 minus 2 pi r divided by 2. The 2's reduce out, so you just get pi r. So now we can take that 500 minus pi r and substitute that to replace the x right here. So now we get rid of the x, so now we can write it in function notation as a of r. All right, so we have 2r, and then instead of x, we're replacing that with 500 minus pi r. So since this now it's in terms of one variable, now this is what we're trying to maximize. So you could take the derivative right now, but if you leave it like this, you have to use the product rule, which is fine. You could do that. But a lot of times if you take the time to simplify it, it makes the derivative easier. So in this case, if we just distribute out the 2r first before we take the derivative, so this is still just a of r. 2r times 500r would give you 1,000r. 2r times negative pi r would be negative 2 pi r squared. And now let's go ahead and find the derivative. Since this is whether you're trying to minimize or maximize, you need the derivative. So a prime of r would equal the derivative of 1000 r is just 1000 minus the derivative of 2 pi r squared would be 4 pi r. And then to find critical numbers, you want to see whether this is 0 or undefined. In this case, there's no denominator or negative exponents, so it's never undefined. Just set it equal to 0. And then to solve this, you could factor out a 4 first as a GCF. And then what we're left with is 4 goes into 125 times, so it goes into 1,250 times, minus pi r. And then 4 will never equal 0. So if we just set the 250 minus pi r equal to 0, we can solve that. So you can add the pi r over to the other side. So 250 equals pi r. And then divide by pi. So here we only get one critical number. R equals 250 over pi. And then we'll draw our number line for the common sense interval here. Which you can abbreviate CSI if you want. So common sense interval is for the radius r. Well, since the radius is a length here, it has to be something positive. So like is a lot of times, to show the lower boundary, 0 with parentheses. But in this case, we're given a perimeter of 1,000, but we don't know anything really about most of the radius could be. So there's not really a known upper limit for the radius. So we'll just put 250 over pi. It's our one critical number. And then label our number line a prime of r, so we'll know what we're testing in. 250 over pi makes it equal to 0. And then here we can test something less than that. That's around 250 divided by 3. But notice 0 is not a critical number, so you could just test 0. If you test 0, that wipes this out in our derivative. We just get 250 minus 0, which is positive. And here you could test something huge, since there's no other critical numbers past this. Test 1 billion or something. So 250 minus pi times 1 billion would be negative. So this shows us the area of the rectangle, A of r. As you make the radius bigger and bigger, it keeps increasing until you get 250 over pi, and then it starts to decrease. So it looks like that if you sketch the graph. So the maximum in this case, there's only one place it could be. It has to be right there at the relative max at 250 over pi. There's nowhere else it could be. And then let's see what it asks for. If it said to find the maximum area, we would take this radius and plug it back in here to find the actual area. But in this case, it just says to find the radius that will maximize it, and we just did that. So the radius would be 250 over pi, and then we just have to put the units on it. The units in this case, since the perimeter is in feet, the radius would also just be feet. It's one-dimensional. And that concludes the notes for AP Calculus on the topic of optimization problems.